So this part of the lecture will be devoted to me giving you general advice on how to learn to write proofs and how to write proofs and how to come up with these things. So there is a risk when you're learning, when you're taking a course like this, that some things might be a little too mechanical, right? For example, there is clearly a sort of kitchen recipe or a cooking recipe for induction, right? Okay, step one, prove the base case, n equals 0. Step two, write down the inductive hypothesis. There's a risk of being too mechanical, and the risk is that if you learn this in a mechanical way, it will be harder for you to abstract it later. You know, what if the base case is no longer 0? Or what if you're no longer dealing with natural numbers, but maybe you're interested in computer science and you have to write a recursion where the induction is done on the complexity of an algorithm, for example, or the steps of some recursive program, right? Then you're not explicitly dealing with natural numbers at all. So this recipe will not really work that way. You have to think about this in a more general way as a concept. And I will do my best to sort of transmit these ideas to you. Of course, I won't be able to do that in just one lecture in the 40 minutes that remain. But keep in mind that writing proofs is a skill. And like any skill, it is a skill that is improved over time by practicing and by getting feedback, right? So you have to form this sort of feedback loop with someone like a professor, like a TA, or maybe just a well-written textbook that contains the solutions. And the idea is that the more proofs you write, the better you become at writing proofs. There's no shortcut or general formula that will always work. Some of the most difficult mathematical problems that have ever been solved, some of them, have rather short, surprisingly short proofs. And the fact that no one ever thought about that for hundreds of years should tell you that there is a complexity or challenge behind writing proofs that goes beyond the context or beyond the having to write a really long or complicated proof. That is not always the case, right? And so some of the problems that I have been selecting for you have been carefully chosen so that we hopefully illustrate some of these examples. So why don't I go ahead and write a few proofs to you and maybe try to guide you through the thought process that goes behind some of these things. So here are some proofs on things that we've defined in the past. Now these proofs aren't that deep, aren't that crazy, but in the following weeks we will cover some really interesting results on number theory, on topology, on set theory, and some of those theorems are actually insanely clever. So stay tuned for those proofs because these theorems, even some of them that are thousands of years old, are far from obvious, and the way you prove them is the way that you expand and gain understanding on how these things work. I think I already tried to motivate the idea, for example, that induction and recursion are kind of the same thing, right? So when you're writing a code that is supposed to compute some solution recursively, then the thing that your brain does shouldn't be that different from how you would prove that such a solution exists inductively in the first place. And I will hopefully try to bridge this gap more. Usually this course doesn't have an emphasis on computer science, but I know for a fact some of you are interested in that, so maybe I can contribute to that a little bit. Also, most of you are mostly interested in learning to write proofs and least interested in the course material itself, right? So maybe listing out a bunch of theorems in number theory is not the thing I should be doing, but rather telling you how would you have come up with this? How could you have come up with this, and how would you write a proof? Okay, so that's now enough of a rant, and let's start writing concrete things on the board. Okay, so we've talked about functions. Here's a very simple exercise. So this will just be a long list of exercises or examples. So first problem or first exercise. Let's say that you have two functions, and let's say that the domains make sense in whatever thing we're talking about. And let's say that you compose them and you get something that is injective. This is related to the quiz, if you're interested. So what can we say? about the injectivity of, let's start with G. I won't really address the case of F because it would just be constructing an example, which can be done with a, with a sketch or something like that. Okay. The composition of two injective functions is injective. But if you take two functions and you compose them and you get something injective, does that tell you that the factors need be injective as well? And I want to maybe convince you that, well, G has to be injective, right? So here's a proof. And if we don't know, this is phrased not as a proof, like prove this. This is phrased as a question. So the natural thing to do is, why don't we try to prove it? And if we get stuck at some point, then maybe the point we get stuck will shed some light as to why this may or may not be true. In this case, I think it will be true. So you say, okay, let x and y be elements in. It didn't say where these functions are defined, so just to cover all bases, let's say in the domain of G. And let's suppose that G sends this element x to the same element as it sends y, right? To prove that G is injective, we would have to conclude that x and y are equal, right? So how would we conclude that? Maybe I can add this as a comment. I will try to make this green to highlight that this is not part of the proof, and erasing everything that's green shouldn't change whether the proof is correct or not. This is just to help the reader, right? This brings me to another point. Writing proofs is a form of communication, right? So there's two phases to it. First, you have to figure out why what you're proving is true and convince yourself that it is true and how you would write this formally. And the second phase is how do you write this in such a way that it is clear. Textbooks and papers use very different language, for example. Papers skip a lot more details than, say, an undergrad level textbook would write. So my advice to you right now, since you're learning how to write proofs, is the more explicit and the more detailed you write your proof, the better. Even if it's tedious to read, even if you write some things that may be obvious or too technical, that is perfectly fine because you're learning how to do this from the ground up, right? So maybe we can do the same here. So let's x and y be. So how do you conclude that x and y must be the same? We haven't used the only hypothesis we have right now, right? Which is that F composed with G is injective. So applying F on both sides. If Gx is equal to Gy, then F will send this element to the same thing because, well, they are the same thing, right? F is a function, so F unambiguously gives the same output given the same input, right? Now, we apply the hypothesis, right? FOG is injective. Okay, I got a question in the chat. This is the domain of F, right? This is the domain, sorry, of G. Apologies if I didn't. I thought I had defined this in the previous lecture, maybe I didn't. So usually when you define a function, you say it's a function from some set A to some set Y. But I don't really want to come up with all these sets because we won't really need them. So the function, the set A, okay, that's great. I think that helps me. Okay, so since FOG, how do you read this in English? FOG? FOG is injective. X and Y must have been the same set. Sorry, the same element, right? And then we're done because that's what we wanted to show. So therefore, G is injective. Right? It is injective because we started by assuming that X is equal to Gy, and we ended up concluding that X and Y must have been the same element. And that's the definition of injectivity, right? Now, we didn't use anything about F other than that it is a function. And you can try doing the same thing. What happens when F, can we prove that F has to be injective as well? And the answer is no. So you can try coming up with a concrete counterexample to this. Let me address things that are more relevant, perhaps, to your problem set, in case you haven't started doing problem set, which is perfectly fine. So let's see about this. Okay, so here's one that would be useful for any sets. For any sets A contained in B contained in X, and a function. Okay, this time maybe I can write it as abbreviation. F will be a function from X to Y. So for any sets, for any function, F, the image of A, is contained in the image of B. Okay, maybe I can do the other part too. The inverse image of A is contained in the inverse image of B. Proof. Did I write proof up here? Yeah, I did. Proof. So if we're very formal, this is quantified with a universal quantifier. It says for all or for any sets. So if I want to be very formal, I have to say let A, B, X be sets as above, such that if I want to be very formal, be set such that A is contained in B, contained in X, and let F be any function, any function from X to Y. Generally, you don't write all the stuff because someone reading the prompt for the exercise would know that, okay, A and B are some arbitrary sets, so you don't have to really repeat this phrase. But in a completely formal proof, then we would have to do this, right, to make it very clear what we're doing. Okay, so let's do these two things separately. So let's say this is part A. Okay. We want to show that the direct image of A under F is contained in the direct image of B under F, right? How do you prove a containment? Well, a containment is proved by taking an arbitrary element on the left, and then we want to show, this should be green. I don't know if I can change the color after I wrote it, maybe I can. Want to show that X is contained in B, right? That's what we want to do. When you are writing a proof, you don't have to add all these green comments. This is for you to know what my thought process is behind this. You can just write the thing in white, So let X be f of A. We want to show that X is in f of B, right? What does it mean by definition for X to be in f of A? It helps when you say every time you conclude something, where or what are you using to conclude it, right? So here we are just using the definition of direct image. It might be obvious, and you don't need to write this down explicitly, because what else could we be using here? But in general, I think it's good practice, right? So by definition of direct image, or I think I just call it the image, whatever. By definition, if X is in the direct image, it means that there exists some A in A. And actually, this is not good practice. When you're writing quickly, like I'm doing now, it's acceptable. But usually, you want to write words rather than symbols because it aids in clarity, right? Unless it doesn't. So there is an element A in A such that f of A gets sent to this element X, right? That's just the definition. I just applied the definition. So what can we do now? So since something happened here. Since A is contained in B, and this is by hypothesis, so we know that this is true. We're assuming that this is true. And we also know that A is contained in A because that's what it says on the line above this one. I know I'm writing too many details, but this is, of course, to highlight a point. I'm making a point. A is contained in B. Then we can conclude that A is also contained in B, right? So f of a is x, where this, where a is an element of b. And this means by definition that x is in the direct image of b, right? You don't have to write this level of pedantic details, but this is how you would write a completely formal proof. The other implication is way easier, so maybe I can leave this as an exercise. Exercise, the inverse image of A is contained in the inverse image of B. This one is easier, right? Because the definition of inverse image is easier to deal with usually. Okay, example number 3. Let's write something a little harder. Let this be an index family of sets. Indexed by some set I could be the natural numbers, and then you would have A0, A1, A2, A3, and so on, right? But it could be indexed by something way more horrible, like the real numbers or something like that, right? Why not? Prove that. Prove that for any function let me think about this, of subsets. And f, again, a function from x to some set that I don't care about y. Prove that. Add some space here so that you can see this. If I take the direct image of the union of these sets, what do you think will happen with respect to, commuting in such a way, in a sense, the symbol union and the symbol of f? So what do you think is the relationship between these two? And there's one of them that you should be able to answer. It's not this one, but it is this one, the intersection. And what do you think about this? Let's say that, let's just pretend that this was given in your final exam. And I'm asking you, decide what containment or equality is satisfied here and how, and prove it, right? So if we have no idea, what we can do is, let's say that we just pretend that we're writing the proof, even though I haven't really figured out what I'm proving. That is fine. Sometimes that is necessary. So how would we prove the first one? I'm not going to write the whole thing again. Let the family, okay? This is just I'm just going to say this. This time I will call it y be some element here, right? So this happens A alpha. So let y be an element there. Can we conclude this? Sorry, I'm getting a question. Answer on Gradescope. As far as I know, nothing has been submitted on Gradescope yet. Problem set 1 is due next Wednesday, and the quiz is due today, but you have until 3 p.m. to do it, and I will give you enough time at the end of this lecture to write it. I believe you can even resubmit if you made like a mistake or something. So yeah, you haven't missed any submissions except maybe last week's quiz, as far as I know. Okay, so let y be an element in this set, in the direct image. That means that, okay, there is some x in the union that has the property that its image is y, right? So by definition of union, and this time I won't be writing all these details, but I'm saying them out loud in case you want to fill in the details. By definition, there exists an index alpha. Maybe we can use a different letter so that you don't get confused that it's the same variable or something. So there's an index, at least one, that contains x, because x is in the union, so it must be in at least one of the unions, right? Okay, so what does that mean? It means that x sorry, that y is in the direct image of alpha beta, right? Because it is the direct image of x, and x is an element of alpha beta. But of course, this is contained in the union of all of them, because it is one of the unions. And so we're done. Y must be an element of that. So far, we proved this containment, right? Therefore, trying to write here. Therefore, we have this containment. Now, if you look at the proof very carefully, you can see that all the steps that I used are reversible. Every step is not just then it follows, but it's actually an if and only if, right? So all these steps, all these arrows, I can point in the opposite direction. So actually, what I can prove is that these two are equal. Now I want you to tell me, what about the second one? Because if you've already taken a look at the problem set, you should be able to answer this. So what about this one? The other containment is similar. What about the intersection? And now that I realize it, I actually made a very small mistake. No, well, actually I didn't. Never mind. It's fine. It's fine. Okay, I want you to tell me what the answer is for the second one. Can I conclude that those are equal, or what containments do you think I will be able to conclude in general? Maybe we can write this down. If you have trouble imagining this so abstractly, try thinking about this with just two sets, A0 and A1. So F of, or A and B, let's say. No containment can be held. Okay, so that is one idea. There is certainly one containment that will hold in a specific case, and you have to prove that in the first problem set. So maybe if that case doesn't hold, at least that containment might not be true, right? Exactly. Okay. So if the function, yes, if the function f is injective, there is one containment that holds. But what about the other? What about the other? Actually, in the problem set, did I write them as equal? I think I wrote them as equal, right? So let's prove the forward containment. Okay. Thank you. Yeah. Okay. In the problem set, they're equal. So let x, well, we call it y. It's a bit nicer, so that it's an element of capital Y. So let x be an element of the direct image of these sets, right? Then let me skip one step, since I've already done a few examples on this. For all, so that there is an x which will be in the intersection. So the step I'm skipping is expanding the definition of the intersection. So there is an x such that for all alpha in I, x is in alpha, in A alpha. It's in all of them because it is in the intersection. And also f of x is y, right? I skipped a small step that's not really that important, so you can definitely write it like this. Now, since f of x is equal to y and x is in all of the A alphas, in particular, for every alpha I, it must also be true that y is in the direct image of alpha, right? Of A alpha. Because x is in A alpha, so this is definitely true. X is already the witness that tells me that y is in the direct image of alpha, of A alpha under F. But if it is in all of them, well, it must be in the intersection, right? So y is in the intersection of all of these. Notice that when I say for all alpha, I'm indexing two different families of sets. The first is the original family of sets, A alpha. The second family of sets that I'm also indexing by alpha and I, is the family consisting of F applied to A alpha. That's a different family of sets. Those sets could be completely different, right? Because F might send them to some weird things. It might send them all to a singleton or something like that. Which actually brings me to the next point. So this proves the first part. Let us try, and emphasis on try on. Did I mess something up? No, I did not. Okay. Let us try proving the other implication. And here is where you will realize how you could figure these things out if you have no idea or you're missing intuition on these things. So the other implication says, and notice that these steps are not reversible, right? So let y be in the intersection of f a alpha. What does that mean? So for all alpha in I, and this is the key part, right? Okay, maybe here I should write all the steps. For all alpha in I, y is in f a alpha, right? That's what it means to be in the intersection. It's in every intersectant. So by definition, there is x and there is x in A alpha such that f of x is y, but this is for all alpha, right? So if x is in all y and all alpha A alpha, my bad, then it must be in the intersection, and y is the image of these, so thus y must be in f of the intersections, right? Is this true? Who can tell me where the mistake is? This proof is wrong, and you can tell this is wrong because in the problem set you're proving that this is true with the additional assumption that f is an injective function. But here I don't know if f is injective. So what is the problem with this? Who can tell me where the mistake is? And this will be the end of the lecture. Any ideas? Okay, very good. So Max says that the same x might not be in the intersection. So here's a problem. We know that y is in f of A alpha. That tells you that x, there is some x whose image is y, but that x will depend on the particular choice of alpha. It doesn't have to be the same x across all of these A alphas. So the problem here is that this is x alpha, right? And then we don't know if we can find something in the intersection of all of them whose image will be y. So everything from here onwards is wrong. And this already tells you how you would try to find a counterexample to this, right? All you have to do is find an example where you cannot find something in the intersection, right? So I'll put a very simple example here. Actually, I shouldn't do that because a counterexample to this is part of the solution for the problem set. So hopefully this helps make sense. So this is wrong. This is wrong, right? Because we don't know this. right? We don't know this. We would know that if f were injective, because if f is injective, then it cannot be, y cannot be the image of different things, right? So f being injective means that y is the image of the same element, basically, and then all the x alphas need to be the same x. And then, of course, we can conclude that that x has to be in the intersection because it is equal to all the x alphas, right, for all alpha. I don't know this. Okay. So hopefully this makes sense. Let me stop the recording here.